My name is Shekhar Mathur,
My name is Kanako Sodagito.
My name is Ash Saha.
and this is our MECH 2502 ball launcher project.
Our project is a simulated ball launcher, and its main objective is to launch balls to a specific distance or a target. It is programmed to launch a variety of balls from different sports such as tennis ball, baseball, basketball, etc. Its function is to launch specific types of ball requested by the user into a distant bin. It is designed in mind to remotely train athletes or anyone for any ball-related sport. It is very cheap and effective alternative to any other traditional forms of training. Furthermore, it does not require any huge space. It's portable and can be easily operated at home or any interior or exterior environment. It can also be used for other recreational purposes such as for maintaining pets, playing with kids. Project details. It's a virtually simulated ball launcher developed through LabVIEW software. The launcher consists of different sizes of balls which are varied in color and weight. Each ball is registered as a different color by the system. There are basically two bins in the system, a pass bin and a fail bin. The user gets to decide what color and mass the ball will for the pass. Anything else will count as fail. Furthermore, the angle that the ball is shot is determined if the passes or fails. 60 degrees will count as a pass, while 45 degrees will count as a fail. The program will calculate the angle and the force to land on a corresponding bin. It is powered by a DC motor and a spring to release the balls with force at a distant target. It has a force sensor to measure the weight and a webcam to check the color of the ball. Materials and equipments. So our project mostly relies on force-sensitive resistor, or also known as a force sensor, the webcam, and two DC motors to set the angle and pull the spring for launch. So for force sensor, it's basically constructed of a servo-themed flexible layers that varies in resistance as well as pressure. A sensor that will detect the force of the ball when stationary and is used to measure and calculate the mass of the balls. It is connected to the DAC system for recording its data. Next up, we have the webcam. The webcam will be used to determine the color of the ball that is placed in the launcher. It is plugged into the USB slot on the laptop and be used in LabVIEW as a vision acquisition system. And then we have the servo motor. It is basically a rotary device that works by sending an electrical output to the motor, which then rotates the pin. Servo motors will aid in changing the angle of the launcher and launching the ball. There's also a spring attached to the motor, which will further store the potential energy needed to launch the ball. Design and concept. So our design is based on the concept of a mechanical spring launcher, which is equipped with two DC servo motors and springs. Furthermore, it's controlled by VI software assisted by a webcam and a force sensor. So how this works is that the LabVIEW software waits for a user input. The input consists of ball specifications, such as the size, the type of ball, and the bin. After receiving user input, the sensing element, which consists of the webcam and the force sensor, detects the right color and finds the size of the ball requested. After receiving the appropriate ball for launch, it sends the output for launch into the motors. After receiving the output signal, it readies the motor and compresses the spring that launches it to its distant target.
So modifications due to the virtual environment. So there have been modifications made to our VI and to our project because of the virtual environment and the predicament that we are in today because of social distancing. So firstly, our program uses visual acquisition software to detect the color and size of the ball. As there's no physical equipment including the DC motor, webcam, and force sensor, these are all replaced by the visual acquisition software to detect the color of the ball and the size of the ball. The DC motors and the actual launching of the ball is done through an animation, and it helps visualize our test case scenarios. As any project has its limitations, ours does too. One of the limitations is that the vision assistant detects images based on a given area of interest in the image. This is set when training the program. For different kinds of balls and different sizes, the vision assistant may need to be trained by detecting a new area of interest for that particular image. Another limitation is that it's only able to compare two masses due to complications with everything being virtual in our case.
For the test cases, the cases were that first, the user will have a choice of choosing what color and or weight of the ball can be shot to the pass bin. All the other balls that do not match the criteria that the user set will be shot to the fail bin. For example, the user chooses the criteria for the ball to be red and weigh 1 kg. The ball is placed, the mass is recorded at 1 kg, and the webcam captures the red ball. It meets all the criteria. The launcher is set to a 60-degree angle and the ball is pulled back. Then the ball is shot and lands in the pass bin. The cases are that the system has to check the mass and the color of the ball and make sure it matches what the user has chosen. Then, it will set the launcher at the appropriate angle and pull back the appropriate length. Then only can the ball be shot. For the calculations, we based our calculations on the second equation of kinematics equations and a velocity equation for the springs. By having the ball at an angle, there will always be two components, an x component and a y component. Having this, we have v naught y is equal to v naught sine theta, and v naught x equals to v naught cosine theta. When we put the second kinematics equation into a y direction, we have that it starts at 0. We have that v naught yt is half t gt squared is equal to 0. And in the x direction, since in an x direction there is no gravity, gravity is then cancelled out. From there, we have x equals v naught cosine theta t, and t is equal to x over v naught cosine theta to further simplify our equation. Once we add the t back into the first equation, we are able to then simplify it even further. Until then, we have it only as the bare bones of v naught equals gx over sine 2 theta. By adding that into the equation of the spring for velocity and rearranging it, we then get this huge equation over here, which is x is equal to the square root of gx over sine 2 theta. Or divide that by the square root of k over m. This will then give us the appropriate length that the spring needs to be pulled back to shoot it to the appropriate bin.
Now we'll talk about the VI and the way it works. So let's explain how this VI works now. In order for the LabVIEW program to identify an image, it needs to use this vision acquisition and vision assistant modules. What the vision acquisition does, in our case, is allow an image to be displayed on the front panel from a folder of images, which will be our test cases. This can be shown over here in this box. There are images of balls of different colors and sizes, which will have to be identified by the vision assistant. The vision assistant can be trained to using different tools to identify the color of the balls or the radius. In order to do this, we set an area of interest on each of the balls and the images of the balls. We do this for the tool to detect the color as well as the tool to detect the radius. Then the vision assistant outputs the color in the form of an array, which has to be broken down into a string, done by this array index function. This is the array that comes out of it, and basically this means that outputs the index 0 string into the string indicator, which is right here. The vision assistant also outputs the radius of the balls through this bundle of information right here. And we use the debundle by name to extract the radius and put it into this indicator. We use the debundle tool right here to put it into this indicator. This data can then be used to compare with each other and decide if the system is passing or failing depending on the user input.
Now I'll explain how the user input works and how we compare the string mass. We weren't able to find a drop-down menu, so we made something that will sort of replicate it. Over here, we have a string control and numeric control. String control is for what the user wants the color to be, and the mask numeric control is what mask the user wants it to be. In order for it to pass, both the color and the mask have to be true. So I took the string indicator from the vision assistant and compared it to what the user chose. Same thing goes for the mask. But since the vision assistant can't give us a mask, we decided to use the radius of the ball by having different sizes of the ball show up on the virtual acquisition system. We made it then so that any radius greater than 80 will be equal to 1 kg, and any less will be equal to 0.5 kg, as shown in this case function. Since we needed both the color and mask to be true, we added an AND Boolean function to achieve that. So if both were true, the true case would run, and if it was false, the false case would then run in this case structure. The formula node is to determine how far the spring needed to be pulled back by using a simplified equation that was shown on the slides from before. That same formula is modified for the false case by changing the velocities for each case, since we already have a predetermined angle. From that, we were able to times it by 100 so we can have it in centimeters and show it on this indicator.
This picture ring animation is used to show if a ball lands in the pass or fail bin. The picture ring consists of 12 images that you can cycle through in order to create an animation. So these are the images in each picture ring. As Sammy explained, if this test case produces a true result, then the pass animation will run, because this is true. The pass animation will run, which is this. The way this runs is by changing it to a picture ring indicator instead of a control. This uses the iterations for the for loop running, which is 12 times, and makes it run through each of the 12 pictures. As you can see, whenever this case structure runs in true, the Boolean has to equal true, which is shown by this Boolean pass LED. Whenever it is fail, the fail Boolean LED will run using this not function. Inside this case structure, the angle also changes based on if the pass animation runs or the fail animation runs, as the ball will be launched at different angles to reach the bins. If it's pass, the animation will run at 60 degrees, and if it's false, the angle should be 45 degrees. This basically sums up the way our VI works. Okay, now we'll show you again what our animation does, as you know how it works now. So we can input any color. Again, let's choose red this time for our test case, and the mask 1. And let's run it. So this is a blue ball, which means it does not validate this criteria, so it's failed. It lands in the fail bin. This is again a blue ball with mass 0.5, so it does not match either of the criteria, and the ball lands in the fail bin. This is a green ball and has mass 1, but the green is not satisfied. That's why it again lands in the fail bin. This is a red ball, but the mass is 0.5, so it does not match the mass criteria, so it again lands in the fail bin. This is also a green ball with mass 0.5, does not meet either of the criteria and lands in the fail bin. This is a red ball with mass 1, which matches the criteria and lands in the pass bin. This is how our VI works.
Potential application. This application can be used during practice and train athletes by schools and sport companies. The technology we use to launch can also be used in the development of kids' toys. The versatility in function of the ball launcher will not only make it cost efficient, but also provide diversity in applications. In conclusion, we will add to the productivity and effectiveness in training professional athletes. We will allow athletes to self-practice their professional sports at home during a pandemic crisis. We will revolutionize testing and training methods of professional sports.
Thank you, and that is our presentation.